Wait, this is part 2 of our discussion under chapter 2, the roots of nonlinear, transcendental, and polynomial functions. So previously we discussed about the graphical method and the incremental search method. So these two types of methods, these are only for searching for the initial guesses. These are only good for searching for initial guesses. So the next two topics that we will be discussing here in this video will be the actual methods that will solve more accurate and through iteration the roots of some polynomials or transcendental nonlinear functions. So first, we will be talking about the bisection method. So bisection method is actually a variation of the incremental search method. And the only difference with the incremental search method, bisection uses the half, the half of the interval of some interval that we already know through the incremental search. That's why it's also called bisection. Is also they also call this one the binary chopping. Some book also name it the Bolzano's method. They call it the Bolzano's method, named after the one that uses this type of method. So basically, bisection method. So if we have here a function, so if this is our function f of x, so we already know that when the value of the function f of x changes in sign, it means that the interval or between those interval there's at least one root. So we said that before. So if our initial guess is, let's call this one the lower value xl and this one the upper value x upper xu. So if we multiply f of xl with f of xu, the upper, if this is less than 0, then the interval xl between xl and xu has if we can locate a root between the interval of xl to xu. So through bisection, we already know this one in incremental search method, but what's the difference with the bisection? So in bisection, so what we do is we have initial guess xl and xu. Then we take the average of the two. So we take the middle point between xl and xu. So how do we take the middle point? We call it xr. Some books uses x of m to indicate that it's the middle point. We can just use, okay, we can just use xm. So first we solve for xm. xm will be equal to the average or the mean value xl plus xu divided by 2. So that's why it's called bisection. We need to bisect the intervals until we meet certain criteria, or if we get exactly if we are lucky, we get the exact value of the root. Then after that, so if we choose xm, this will be our new xm. Now after determining xm, we need to know where is the root. Is it between xl to xm or xm to xu? So obviously in this figure, this is our root. So from here, we will change again our interval. So how do we know that the root is at the right side of the interval, or the left side, the lower part, or the upper part? So if you draw the figure, you can see it directly, but it's not a good practice that every time you solve them, you draw the figure. What if I cannot draw the figure because of limited time, or I don't have any software or calculator that we'll be using to graph this one? So how do we determine? So what we do is we multiply the f of m. You substitute m to the function. First, we multiply it with the lower f of l, xl. This is xm, f of xm, f of xl. So if this is less than 0, so what does it mean? If we multiply f of xm and f of xl, so where does this f of xm? Here, this is our f of xm, and this is f of xl. This is f of xl, and this is f of xm. So obviously, if you multiply them, they are both negative. They're below the x-axis. So it's not less than 0. So if it's less than 0, then the root is in that interval. If it's less than 0, the root is between xm to x, or xl to xm. Otherwise, if it's not less than 0, it's greater than 0, then the root is not cannot be located between xl to xm. So next, we check for the other interval xm, the other part xm times f of xu. And again, if this is less than 0, then the root lies between xm to x upper. So this is bisection. So if we look at the drawing, the product between f of xm and f of xl is negative, is positive because it's negative times negative. F of xl, this one is negative, this is also negative. So they are both negative. If you multiply them, you get a positive. So therefore, the root is not in that interval. So we disregard this interval. Then we check again to the right side, to the right interval, xm and xu. And we know this is x of u, f of xu. F of xu, if you project to the y-axis, this is a positive value. F of xm is a negative value. So if you multiply that, it's a negative. So conclusion, the root is within xm to xu. Now, question, what if f of xm times f of xl is exactly equal to 0? What if it's equal to 0? Then if it's equal to 0, then xm now will be the root. Then xm is the exact root of the function. Because if it's 0, then it means that one of them is 0. Or f of xm is 0, not f of xl, because this is our interval. Also, f of xm times f of xu is also 0, because this is 0 and this is 0. So if that is 0, then it means if the function is 0, it means that the value for x is the root of the function. So you stop there. That's already the root. So this is the algorithm of the bisection method. That's why it's called the binary chopping. We chop them either to 2. That's why it's called binary, upper and lower, upper and lower. And until you get the more accurate value for the root. So after that, f of xm and f of xl. So your new lower value now your new xl now will be xm. Here, this will be your new xl, and this is still your xu. So if I solve again for xm, this will be our new xm. New xm here. So if we do that again, then the interval will be between xl and xm, not xm and xu. Then you chop it again until you find the root. So if we write the algorithm, so these are the steps. Step 1. So let's summarize the steps. The first step is to choose uh, the upper and the lower guesses. Choose X, L, and XU. So when choosing XL and XU, you take note that if I multiply XL, f of XL, and f of XU, this should be less than 0. Otherwise, my lower and upper interval limits are the roots cannot be located between that interval. You change the interval. So the best step 1 is to do either graphical method or you do incremental search. Sometimes the problem says the exact interval for the root. But take note of that. F of xl times f of x is less than 0. There are times that when the problem says that it's from 1 to 3, but if you not multiply them, if you don't know that it's not less than 0, it's greater than 0, you do the step 2, 3, 4, and so on, you're just wasting your time because there's no root between that interval because it's not less than 0. So if it's not less than 0, stop. Change the interval. Then if it's less than 0, then go to step 2. So step 2 is to estimate the root. So we need to estimate the root. So how do we estimate the root? Solve for the midpoint. XM. XM will be XL plus XU divided by 2. So step 2, determine the midpoint or estimate the root. This will be our estimated root. XM. Estimated root. And after estimating, we compare. This is step 3. This is what we did in the first part. So how do we compare? So A, there are 3 cases here. Case A is when f of xl times f of xm is less than 0. So what do we do if this is true? If x of xl times f of xm is less than 0. So we said before that if it's less than 0, meaning the interval, that interval, there is a root located on that interval. So here, if it's less than 0, therefore between xl and xm, there's a root. So what we do is we change our new value for the lower and the upper value. So if this is true, retain xl, we retain this value, but we change our xu and we make it equal to xm. We make our x upper to be equal to our new xm. And after that, after doing that, return to step 2. Return to step 2. Do it again. But if it's not less than 0, you check the next one. You go to the second case. If f of xu times f of xm is less than 0. So if this is less than 0, what do we retain? We retain x, what? Xu or xl. So if you look at the figure again here, so this will be our interval. So we will be retaining f of xu or xu. Then we will change our lower limit or value to be the midpoint. So xu will be retained, and the next, our new lower limit now will be equal to the xm or the midpoint. Then After doing that, you return again to step 2. Then the third case is when it's exactly equal to 0. XL times f of xm is exactly equal to 0. Then therefore, xm is the root. Xm is the root. So you can now terminate the computation. So that's the basic algorithm of a bisection method. Now we will apply this one in solving our previous example before. That's our previous example. But before that, how about our stopping criterion? So remember our stopping criterion, epsilon of x. This is equal to 0. Forget the formula. 0.5 is 0.5 times 10 raised to 2 minus n. So this is in percent, where n is the number of significant figure. So it's still applicable here. This will be our stopping criterion when epsilon a, our approximate error, is less than the stopping criterion, absolute value. So how do we solve for the approximate error? Approximate error is still equal to the difference between the previous and the new value divided by the previous, or the new value, times 100. So this will be equal to absolute value xm, the new xm, the recent, minus the previous one, xm old, all over xm new, and times 100%. So this will be our approximate error. So whenever this value is less than the pre-specified stopping criterion, then we can now stop the iteration. So let's try to solve some example. Let's use our previous example. F of x equals x cubed minus 0.3. So we already know the actual value of this one, the true value. So this is it's much easier for us to solve this one as our example. But in your exam will be it's more difficult than this one. But it's still the same method, the same steps. The only difference is the calculation, how you calculate the values, but still the same. It's not different. The only difference is the equation. You can use your calculator, so it's still the same. So here we need the stopping criterion. We need to specify our stopping criterion. So let's say our n up to 4 significant figure. Let's just use 4 significant figure. Sig p. You can use more than this one, but to minimize our iteration, I just use 4. So if n is equal to 4, so what will be our stopping criterion? So this will be equal to 0.5 times 10 raised to 2 minus 4%. So 2 minus 4. So the stopping criterion will be equal to 0. So raised to negative 3, 5 times 10 raised to negative 3. This is 0.005%. So we stop for iteration when our approximate error is less than 0.005. So let's do that. So first step, what's our first step? Our first step is to choose our upper and lower value, XL and XI. Let's just make a table. It's much easier for us to solve this type of problem or methods if we use a table. So XL and XU. This is the number of iteration. Then what do we need? We also need to evaluate the function at XL and at XU. And after that, we take the midpoint, we take XM, then we evaluate that one, then later on we will multiply it with either XL or XU. Then we can proceed to repeat step 2. Then we also need to solve for the error, approximate error, absolute value, PA. Okay, so first iteration, number 1. This part. So what should be our initial values for our initial guesses, XL and XU? So we solved this before in the first incremental search. We know that the root is between 0 and 1. But if you don't know that it's between 0 and 1, you can make it from 0 to 3, or you can make it wider. The solution will become more solution, but that is impractical. But to avoid that one, because we want to limit our time here, so we will be using from 0 to 1. So our interval is from 0 to 1 because we know it's between 0 and 1. The next, so we evaluate what will be f of xl. So we substitute 0 here to our function. So 0 cubed minus 0.3. So that will be equal to negative 0.3. Then for the upper, 1 cubed minus 0.3. So 1 minus 0.3 is 0.7. Then xm, what's our xm? Midpoint. We just take xl, we add it with xu. 0 plus 1, then we divide it by 2. So 0 plus 1 is 1 divided by 2. 0.5. Then we evaluate, we substitute 0.5 cubed minus 0.3. The answer will be negative 0.175. So you don't need to write 0.175. You can just take the sign here because the sign is what we need, so that we will know what to retain and what to change for our new upper and lower values. Next, so we don't need to solve for epsilon or the approximate error here because we don't have the previous value for xm. So next, number 2, iteration 2. So what will be our new xl? What will be our new xu? So it depends. It depends on what. Remember our cases. If it's less than 0, f of xl times f of xm is less than 0, retain xl. Then change xu to xm. But if f of xu times f of xm is less than 0, we retain the other one. Then we equate it with xm. It's equal to 0, then that will be the root. So here, our xm, f of xm is negative. So first, we multiply it with f of xl. So negative times negative, it's positive. So it's not less than 0. So it's not case 1. So it's not case 1. It's not this one because it's greater than 0. For the f of xu times f of xm. So 0.7 times this negative, so it's negative. So it's less than. So we use case B. So what is case B? We retain the original x upper, but we change our xl to xm. We retain our original xu, then we change our xl to xm. So this will be 0.5. Okay? So that is bisection. Then we do it again, repeat it again. So what will be f of xl. Our f of xl now will be the last here, f of xm. Just copy this one, 0.175. Then for f of xu, still the same, 0.7, because f of xu does not change. But our xm now will be different. So what we do is we add 0.5 and 1. So 0.5 plus 1 is 1.5. We divide it by 2, then we get 0.75. Okay, what will be our f of xm? Our f of xm will be 0.75 cube minus 0.3. So it will be 0.1219. Doesn't matter. The sign, you only need the sign. And we can now solve for our approximate error. So our approximate error will be 0.75 minus 0.5 divided by 0.75 times 100. So that will be 33.33. So this is in percent. So still far away from 0.005. And for the next part, the third iteration. So what will be our lower and upper limits or values of the intervals? So first we check the cases again. F of xm, we multiply it first with the lower. If it's negative, then we retain the value for case 1, retain xl. So if you multiply it with xl, it's negative, you retain xl. If you multiply it with xu, it's negative, you retain xu. This is the pattern. So here, if you multiply f of xm with f of xl, it's already negative. So we retain xl. So this will be still 0.5. But what will be our new xu? It should be equal to the old xm, which is 0.75. Then again, we compute all of this. We just substitute these values here. We came up with for f of xl this still the same, negative 0.175. F of xu, it's the same as f of xm, 0.1219. So you can make it just the sign. You can just take the signs here, f of xl and f of xu, because that's what we need. We just need the signs. Or if it's equal to 0, then that's the time our root is located. So we continue. Our new xm now will be equal to 0.5 plus 0.75 divided by 2. So that will be 0.625. Then, before we do that, let me first make this one bigger. This is xm. 0.5, 0.75, 0.625. Then what will be our new f of xm? So we substitute 0.625 to the function. So the answer here is negative 0.056. And after that, we solve for we test if we already met the stopping criterion. So we just subtract 0.625 to 0.75. We divide it by 0.625. And it should be a negative, but it's an absolute value. And that's equal to 20%. Alright, next. So, medyo malayo pa for the stopping criterion, which is 0.005. We go to the next one, number 4. So we still need to continue our iteration. So we go to the 4th iteration now. So for the 4th iteration, what will be our lower and upper limits? So we check the product again, f of xm times f of xl. It's positive. So we don't retain that one. But if you multiply it with xu, f of xu, it's negative. So we retain f of xu, 0.75. Then we change this one, xl, to the xm, so 0.625. Then solve it again, all of them. So this will be 0.625 was 0.625 xm, negative 0.056. Then for xu, it's still the same, 0.121. Then for xm, we add 0.625 and 0.75. So the answer will be 0.6875. And for f of xm, this will be a positive value, 0.025. Then we solve for the approximate error between 0.6875 minus 0.625 divided by 0.6875. So that will be around 9.09. So still far away from 0.005. So we need more iteration. So this is a very tedious method to solve this one because we want up to 4 significant figure. So the higher the number of significant figure that you want to be accurate, then the more iteration you will be doing. So you can use Octave or MATLAB in this one. It's more practical to use these methods through computer applications. Or you can also use Excel because this is in tabular form. Excel will be a very good tool, or Google Sheet if you have Google Sheet. So let's continue. How many iteration is this? The fifth iteration. Let's do this again. So 5. What will be our XL now? F of XM is 0.025. Then you multiply it with XL, so it's negative. So we retain XL, so 0.625. Then we change XU with the previous value of XM. Then F of XL, and so on. So repeat this process until you get less than 0.005 approximate error. So we need to pause this one. You can do it. Then this will be our result. So I will just give you the result. So this will be the final result. Now I'd use Google Sheet para mas mabilis yung computation ko. So this one, this part is XM. This L, XU. So this will be our final answer here. This part here, 0.669403762. So it doesn't matter. We only need the 4 significant figure. Why do we stop? Because our epsilon A now is 0.004559. So it's already less than 0.005%. So we check if this is really accurate up to 4 significant figure. Let's try to solve again. So this is our true value for x. It's equal to 0. Let's try to compute it again. Cube root of 0.3. 0.669 4329,501. So if we can't count our number of significant figure, 0, 6, 6, 9. So that's 4. So we only need 0.669 so that we can say that our answer is accurate. So if you look at our answer is 0.669, so that's accurate. And there's a bonus because the criterion, Scarborough criterion, has a allowance of another one significant figure for the final answer. So here we have actually 5 significant figure that is accurate. So that is bisection method. You can save more time here if you use applications. And the next one, the last bracketing method, the false position method, it's also a variation of this one. It uses less number of iterations. That's the advantage. The disadvantage is instead of using the midpoint or the average, or we have the interval, there's a formula that you need to remember. You need to memorize the formula for that method. So we will be talking now about the false position. False position method. So it's almost the same with the bisection. The only difference is the formula for xm. It's not the average. It's not equal to xu plus xl divided by 2. It's a different value. So if we try to derive that one, say if we remember, so let's derive that instead of the midpoint here. So if this is our interval and this is our function f of x. So this is our root. And this will be our midpoint here, xm. Instead of using this one, xm, instead of taking the average, so what we do is we take a triangle connecting the lower and the upper. So here, if I draw something here, instead of taking the average, so this is now not our average. Now we can now just call it xr, not xm. So what we do is we connect this one here, this point here, to our point here. This will be our lower, and this is our upper. Then this is a triangle here. We have a triangle here. And we also have another triangle, small triangle here under the x-axis. Then this point now, here, the intersection, this will be our assumption or approximate value for the root. And let's just call it xr. And we can observe that the bigger triangle is similar to this smaller triangle. So to derive the formula for false position method, you don't need to memorize. You can memorize, then memorize it. But you can derive it again. Remember this one, this is the derivation. So we use similar triangles to derive. So what will be this length from here to here? What is this length? This is actually what? F of x u, which is our xu here is, our x value here is xu. So this length is f of xu. Then how about the smaller triangle? For the smaller triangle, the height is f of xl, f of xl. Then for the bases of the triangles, so here and here. So first, this one, what is this length here? What's the length of this base? This one is xl from here to here. This is xl. And this is xr from here to here. So if we solve this one, it's just equal to xr minus xl. It's just equal to, so this length now will be just equal to xr minus xl. And for the bigger triangle, so this length now will be again from here to here. This one is xu. And from here to here, this is xr. So therefore, this length from here to here, the base of the triangle here will be xq minus xr. So that's the length of the base of the triangle, bigger triangle. Then by solving x of r here, so the formula for x of r now will be equal to, you can use algebra. Then the final will be this one, xr is equal to xu minus f of xu times x of l minus xu all over f of xl minus f of xu. So this will be the formula of x of r. Instead of using xm in bisection method, in bisection method we use xm equals x plus xl divided by 2. So this is in bisection. This is only the difference of the two methods. In bisection, you use this one. In false position method, we use this one. It's the same method, the only difference is the formula in solving the approximate value. So we can again solve our previous example. Then let's look if how many iteration we'll be using. Example, f of x is equal to x cubed minus 0.3. And our epsilon stopping criterion is 0.005%. So let's do this again. So solution. So what will be our first step? It's the same steps. So again, first step is we need to choose our the upper and the lower. X, L, X, U. Then we need to know the values of the functions at these x's. F of xl, f of xu. Then after that, we instead of taking the midterm now, midpoint, we take the x of r, which is the formula, the derived formula from above. Then we also take f of xr. And we will compare that one with f of xl and f of xu. Then our stopping criterion in percent, our approximate error. Then we do it again, just like what we did before in bisection method. So first, again, we choose from 0 to 1. First iteration, 0 to 1. Next, what is f of xl? It's the same, 0.3. This one is 0.7. And how about xr? xr, we use the formula. What's the formula? xu minus f of xu times, or minus f of xu times xl minus xu all over f of f of xl minus f of xu. So the answer here will be around 0.3. Then for f of xr, it's negative 0.270. And we don't have yet our approximate error. Next iteration. So we multiply f of xr with f of xl. So it's positive. So it means we need to change that. Change it with 0.3. So f of xl here now will be 0.3. Then for our xu, we retain xu1. So what will be our new f of xl? This will be equal to negative 0.273, and f of x is still the same, 0.7. Then we substitute again 0.3 to our formula. You will arrive with 0.496402. Then f of xm is negative 0.1776. And the approximate error will be around 39%, 39.5 or 39.6%. Next, third iteration. So f of xr is negative, so you multiply it with f of xl, it's positive. So again, we change xl to our new xr, which is 0.496402. And we retain this one. So f of xl now will be negative 0.1776. Then this one is still the same, 0.7. Then what will be our new xr? You substitute this one again to the formula. You will arrive with 0.59835. And here, this is negative 0.8086. And the approximate error now will be 17%, around 17%. Then we continue, and so on. So the number of iteration that we will be doing here is actually it's 12 iteration. It's lesser compared to the first one. So this will be our result. From the third iteration upward to the last. So this will be the result for the 4th, 5th, until up to 12. So if you can observe, xu does not change. So this makes our computation easier because we only change xl. We don't go more than xu, or we don't change xu. And we stop at 0.002% approximate error, and this is the answer, 0.66942, and it's still accurate up to 1, 2, 3, 4 for significant figure, and also the bonus, the fifth one. So that is false position method. So in our next discussion, we will be talking about the other types of root finding techniques. So these previous methods, these are called the bracketing methods or the closed methods. The next one will be the open method or the non-bracketing. So those non-bracketing are somewhat similar, but we don't bracket, we don't limit ourselves from XL to XU. We don't choose intervals, but we find the roots wherever the roots is. So, okay, so this is part 2 of chapter 2 and continuation of the bracketing method. We will also implement these methods in Octave in our laboratory. It's better, you can appreciate them more if we use them through applications. You can use Excel or Google Sheet, but in our lab, we will be using Octave or somewhat similar to MATLAB. Any similar MATLAB uh, applications, because we will be creating our programs. We write them without GUI. We don't need GUI. We just need to code them and then run them through the command window. So